In this module, we'll be discussing discriminant analysis and classification. Remember that we had been looking at grouping of data or clustering in the previous modules. Now, the clustering methods were primarily exploratory by nature. By this, we mean that when you do clustering, you do not have any predetermined idea about what clusters are or how many clusters there are. So we actually look at the n individuals and then segregate them into some undefined number of clusters or undefined clusters, and then we form these clusters. And then we need to distinguish among these clusters. As opposed to this, in discriminant analysis and classification problems, we have distinct, well-defined clusters. So what we need to do in discriminant analysis, we don't need to form the clusters anymore. What we only need to do is to identify individuals with the different clusters and then to distinguish between the different clusters. So we need to answer the question as to why one cluster is different from another, how to differentiate between these two, and in the classification rules we will need to also find out what happens to a new member. Which group should we be putting this new member into according to his characteristics? That is what we do in discriminant analysis and clustering. So it is not exploratory by nature, but it is rather a confirmatory type of method that we use. To begin with, we first need to distinguish between discriminant analysis and classification rules. The technique for distinguishing between well-defined groups or clusters is referred to as discriminant analysis. So what it does is it separates observations into different groups and identifies the differences between these groups. So once we do the discriminant analysis part, we have the distinct clusters with their distinct characteristics. In the classification rules, what we do is we allocate new observations into one of these groups. So when a new allocation comes, a new individual comes in, which of this well-distinguished group that we need to place him? That question is answered by the classification rule. In fact, when we actually do this, discriminant analysis and classification, the distinction between these two becomes a little bit fuzzy. So one leads to the other, therefore we'll be looking at them simultaneously, and once we have a classification rule, this rule itself can be used as a discriminating factor between the different groups. Now let us look at an example. For example, we are looking at job applications. For job applications, we seek the age, the gender, the skill, the job experience, educational qualifications, and other qualifications of the individuals applying for the job. The question here is how to decide who will be competent for the job and who will not be competent for the job. So how to discriminate between the competent group and the not so competent group. That would be the discriminant analysis part. The second part would be how to select an interviewee. So there would be people coming in and you take interviews of these individuals. What are the criteria which will determine whether this interviewee is competent for the job or not? You can see that there are several criteria, so it's not very easy to determine on the basis of those. So we have to summarize all these different variables and come to a decision of whether considering him as competent or not considering him as competent. Let us look at another example. So when you go to a doctor, the doctor asks you to go for medical tests. And you look at the blood pressure, which is the systolic pressure and the diastolic pressure. You look at the blood sugar level, you look at the hemoglobin level, you look at many other pathological test results. Now the question is, how does the doctor decide whether the person is healthy or not? You see, in some cases, maybe the blood pressure is high, but the blood sugar level is normal, the hemoglobin level is normal, etc. So you have different criteria for different individuals. And some of these individuals are healthy and some of them are not. So how do you distinguish between these two groups of individuals? And secondly, when a new individual or new patient comes to the doctor looks at his different pathological results and then has to decide on the group that the new individual should be placed into, whether this new individual should be considered as healthy or not healthy. So again, a problem of classification would come in. To begin with, let us look at a very simple case of two populations or two groups. Now, there are n individuals each with m characteristics, say. So x is equal to x1, x2, xm, each of the xi's representing a characteristic. So we have a vector of m variables characterizing this individual. These individuals come from either of two groups, G1 or G2. So we have two distinct groups we know of, and all the individuals belong either to one of this group or to the other of this group. The groups are again characterized by some probability function, say f1x or f2x. So they have distinct characteristics. G1 has the characteristic f1x and G2 has the characteristic f2x, which distinguishes it from G1. Also, the prior probability that an individual belongs to a particular group is given. So it's either P1. P1 is the probability that an individual comes from group 1, or it is P2, where P2 is the probability that the individual comes from group 2. So since all individuals must come from one of the two groups, it's obvious that P1 plus P2 must be equal to 1. Now, how to identify the individuals with the groups? So what we do here is we look at the sample space, which is the total possible values of x. So omega is the sample space, and we partition this sample space, so the probability or the totality of all x into two subsets, R1 and R2. These two subsets are so chosen that they are mutually exclusive and exhaustive. That is, R1 intersection R2 is phi and R1 union R2 is omega, which really means R2 is omega minus R1. What does this mean? They are mutually exclusive means that an individual can either belong to R1 or to R2, but not to both. And exhaustive means that the individual must belong to one of the two groups, R1 or the R2 group. Okay. The rule is, so we define a rule this way. If x belongs to R1, we assign x to the first group. If x belongs to R2, we assign x to the second group. The classification rule also is same. So a new individual comes in, we see in which region this observation falls. If the observation falls in the region R1, then we classify these individuals in the first group. If the observation falls in R2, then we classify the individual into the second group. So this is the decision rule that we decide upon. The question, of course, is how to split omega into R1 and R2. You see, once we have decided on what R1 and R2 is going to be like, the classification rules become easy, because now we know what R1 is, what R2 is, see where the individual lies, and then assign him to the corresponding group. So the splitting of omega is the more important thing. Now omega is split on the basis of what we referred to as misclassification. Misclassification is assigning a member to a wrong group. So incorrect assigning of an individual is referred to as misclassification. Now what can happen is one of four things. You can have a member from group 1 and who is assigned to the first group, and in that case we have a correct classification. You have a member from group 2 who is assigned to the second group, again we have a correct classification. But if a member from the first group is assigned to the second group, we have a misclassification. Similarly, a member from the second group assigned to the first group is a problem of misclassification. So what we need to do is to minimize the probabilities of this misclassifications. So the chance of misclassification should be as small as possible. So you choose R1 and R2 in such a manner that this misclassification probabilities are as small as possible. Now, how to do this? To do this, first of all, let's look at the conditional probabilities of misclassification. Why we call it conditional? Now, remember that individuals come from only one of two groups, G1 and G2. So, the conditional probability of misclassifying an individual coming from G1 to G2 is probability of 2 given 1, which is x belonging to R2 given G1. It's given G1 because the individual comes from G1, and x belongs to R2 because he has been assigned to G2. Therefore, x must have been in R2. So, what is the probability that x should belong to the region R2 given the fact that the individual has come from G1? This is given by the integral of f1x dx, which is the characteristic of the first individual. This integrated over the region R2, this x falling in R2. Similarly, the conditional probability of misclassifying an individual coming from G2 to G1 is given by P1 given 2, and which is the probability of x now belonging to R1 given the fact that the individual comes from group 2, and this is the integral of f2x dx over the region R1. So these are the two conditional probabilities of misclassification. To find the unconditional misclassification probabilities, the probability of misclassifying an individual coming from G1 is that the probability of his lying in R2 given that he has come from G1 into the probability of his coming from G1. So it's basically an intersection of two things. The individual comes from G1 and he has been classified into the region R2. So as you know, you can always write this intersection of these two events as probability of the first event P1 into probability of the second event given the first event, which is probability of x given falling into R2 given G1. And the first part is P1 and the second part, as we have seen before, is the conditional probability of x belonging to R2 given G1 is P2 given 1. So it's P1 into P2 given 1. Similarly, the unconditional probability of misclassifying an individual coming from G2 is P2 into P give 1 given 2. Now there are several classification rules. The simplest but not probably the best rule is the total probability of misclassification rule. By the total probability of misclassification is meant the probabilities of the two misclassifications. So what is the probability of individual is misclassified as G2 and the probability that the individual is misclassified as G1. As we have seen, the first of this is given by P1 into P2 given 1, and the second is P2 into P1 given 2. So what we need to do is, we need to find the minimum of the TPM, or the total probability of misclassification. That would lead us to an optimal rule. However, the TPM does not take account of the costs of misclassification. Now, cost of misclassifications is important. Let's look at an example of this. This cost may not always be the same. For example, when you go and buy some item, if you buy a defective item as good, you think it is good, but it is not, you have a certain cost associated with this. But if you don't buy a good item thinking that this is bad, probably the cost is much lower. In the first case, you have spent money on something which is not good. In the second case, you could have bought something you like, but you have forgone it, assuming that this is not good. So the cost of these two definitely are very often not equal. So there has to be a cost associated with the two types of misclassifications. Now let C2 given 1 be the cost of misclassifying a member from G1 into G2. So it's given G1, he comes from G1 and has been placed into G2. So the cost of this is C2 given 1, and similarly C1 given 2 is the cost of misclassifying a member from G2 into G1. Now a classification rule based on what is referred to as the expected cost of misclassification is given this way. So first we need to find the expected cost of misclassification. Now when you find expected cost, it has to be the cost of misclassifying an individual from G1 to G2 into the probability that the individual is misclassified as G2, plus the cost of misclassifying an individual from G2 into G1 is into the probability that the individual is misclassified as G1. And this, as we have seen before, is probability of individual is misclassified as G2 is P1 into P2 given 1. So we simply multiply it by C2 given 1, and similarly for the second part. And so the expected cost of misclassification, or ECM, is the sum of these two components, P1 into P2 given 1 into C2 given 1 plus P2 into P1 given 2 into C1 given 2. And what we need to do is to find R1 and R2 such that the ECM is minimized. Now, the result that actually gives a rule of, or a distinction between R2 and R1 which minimizes the ECM is as follows. R1 is given by f1x by f2x greater than or equal to p2 by p1 into ratio of c1 given 2 by c2 given 1, and R2 is given by the complementary region, which is f1x by f2x is less than p2 by p1 into c1 given 2 into c2 given 1. Now what are these? On the left hand side we have f1x by f2x, which is the ratio of the two densities, and on the right hand side we have two ratios. The first of this, p2 by p1, is the ratio of the prior probabilities of coming from one or the other of the two groups, and the second is the ratio of the two costs. So what we do to find a minimum ECM is to relate the ratio of the densities with the product of the two ratios of the prior probabilities and the cost. If the first is greater than the second, then we place the individual in R1, If the second is greater than the first, then we place the individual into R2 and hence into the second group. Some of the special cases here is, firstly, the cost may be equal. So if you have C2 given 1 is equal to C1 given 2, then the results actually reduce to f1x by f2x greater than equal to p2 by p1 is the R1 region, that is you place the individual into G1, and f1x by f2x less than p2 by p1 is the R2 region, that is you place the individual in G2. Now if you look at this result and if you see how this result comes, it's basically when you take the cost equal, that is in this case you are ignoring the cost because they are equal. So what should this lead to? Obviously this should lead to the minimization of the total probability of misclassification. So the rule obtained by minimizing the total probability of misclassification comes out as a special case of the minimum ECM rule, where the two costs are equal. Two other special cases. First of them is when the prior probabilities are equal. So if the chance of coming from either of the two groups is half, then f1x by f2x would be simply dictated by the ratio of the two costs. So f1x by f2x greater than c1 given 2 by c2 given 1 places the observation in the first group, and the ratio being less than c1 given 2 by c2 given 1 places the observation in the second group. A third is the case of both costs and prior probabilities being equal. It simply reduces to the ratio being greater than or less than 1. So if it's greater than equal to 1, you place in the first group. If it's less than 1, you place in the second group. So this all comes out as special cases of the ECM minimization. Now let's look at a very simple example. Suppose we have a population G1 which is characterized by the density function f1x, which is an exponential distribution with mean 5. Similarly, we have a second population G2 which is characterized by an exponential distribution with mean 8. And we need to place individuals in one of these two groups. And we are also given the misclassification costs. So if an individual from group 1 is misclassified and placed into group 2, we have a cost of 12. On the other hand, if an individual from the group 2 is classified into the first group, then we have a misclassification cost of 15. Suppose the prior probabilities of coming from the first group is 0.6 and from coming from the second group is 0.4. So again, the sum must be 1. The individual should come from one of these two groups. So the first group has a probability of 0.6 and the second a probability of 0.4. Then the rule is to assign to G1 if f1x by f2x, which is 1/5 e to the power of minus x by 5, that is the exponential density, divided by 1/8 e to the power of minus x by 8, which is the exponential density under mean 8, is greater than equal to the ratio of the two prior probabilities, which is 0.4 by 0.6, into the ratio of the two misclassification costs, which is 15 by 12. You assign to G1 if the left hand side is greater than the right hand side, and you assign to G2 if the left hand side is less than the right hand side. If you simplify this, then we assign to G1 if x into 1/8 minus 1/5 is greater than log of 6 into 5 by 7.2 into 8. So what we did here was just to take expectation. So rather we took log in this case. So the left hand side actually came out to be x into 1 by 8 minus 1 by 5, and the right hand side is log of this number 6 into 5 by 7.2 into 8, and this on simplification gives R1 as x such that x is less than 8.6973. Obviously R2 would be x such that x is greater than or equal to 8.6973. Interestingly, you will see that there is a change in sign in the direction of the inequality in case of R1. This is because if you look at the assignments, you have x 1/8 minus 1/5, which comes out as negative simply, and the right hand side log of 6 into 5 by 7.2 into 8, which is a fraction. So if you take log, it comes out to be negative, and hence the inequality sign is reversed, which is probably, given the problem, this is more realistic because you have mean 5 for the first group and mean 8 for the second group. So the smaller the observation, they should be going into the first group. The larger the observation, they should be going into the second group. So what happens here is, suppose we have two new observations. So first one of them is x0, which is 8, and the second of them is x0 star, which is 9. Now let's look at the first observation, x0 equal to 8. We assign x0 to G1 because x falls in the R1 region. 8 is less than 8.6973. It falls in the R1 region, and hence x0 is assigned to G1. As for the second observation, x0 star, this is 9, which falls in the R2 region, being greater than or equal to 8.69, and hence we assign x0 star to G2. This is how we assign the individuals once we have decided on the R1 and R2 regions. So what we have seen is we can use either the expected cost of misclassification or the total probability of misclassification, and then subdivide R1 and R2 into two mutually exclusive and exhaustive regions, and then look at, you see in this case the first part, dividing this, getting this R1 and R2 is the discriminant analysis part, and when you come to the last part of putting x0 or x0 star into one of these groups, you are actually looking at classifying new individuals into the well-defined two regions. But this problem is simple because we are looking at a single variable. When we look at more than one variable, when you have a vector of characteristics concerned with each individual, the problem becomes slightly more difficult. And that is something we'll be looking in the coming modules. In this module, we have discussed discriminant analysis and classification. We have given an introduction into the two methods. Primarily, discriminant analysis is based on the probabilities of misclassification. We have defined the different types of misclassifications that we may have, and what we did then was to distinguish between different types of rules based on this misclassification probabilities. The rules are primarily either the minimization of the total probability of misclassification or the expected cost of misclassification. We have done these two different types of rules, and we have looked at an example where we can distinguish between individuals based on these rules. So in the future classes, we will be looking at different distributions and how the different distributions can be distinguished through the discriminant analysis technique.